In this video, I just want to talk about an example exploratory analysis, just to show kind of the tools that you might want to use when you're just starting out looking at data. So a lot of these things are basic, things that we've covered, like, one-dimensional plots, two-dimensional plots, basic summaries, exploratory plots, just to get a sense of what the data look like and what you might be able to do with them. Now, the first thing, of course, anytime you start to look at data, is you have to have a kind of a basic idea in mind of what you're looking for. This can come in the form of a hypothesis, or even more generally, just as a basic question. What are you trying to answer with this data set? So the data set that I'm going to use right now for this example comes from the U.S. Environmental Protection Agency, and it involves air pollution monitoring data from the United States. In particular, we're looking at fine particulate matter air pollution that's in the air. So particulate matter is just a fancy word for dust. So this is just dust that's in the air, and it's of concern because we inhale air all the time, and along with the air we inhale the dust, and it may have certain health effects on populations. So one of the important pieces of legislation in the last 4 decades in the United States has been the Clean Air Act. And the Clean Air Act has been designed to reduce the levels of air pollution in the United States. And so one of the questions that you might want to ask when it comes to these kinds of data is, are air pollution levels lower now than they were before? Right, so it's a very basic question. It's fairly general. We can look at it in a variety of different ways, and so we're going to look at it in a very specific way. We're going to look at a fine particle air pollution, and so this fine particle air pollution was started being measured in 1999, and is currently being measured today. So what we're going to do is we're going to look at data from 1999 and look at the fairly recent data from 2012, and we want to answer the very basic question: are the levels on average lower in 2012 than they were in 1999? And so the nice thing about air pollution data in the United States is that the EPA collects all of this data and makes it essentially all available on their website. So it's freely available. I'll put the URL up on the website, and you can download as much or as little as you want. So what I've done is I've gone to the EPA website and I've just literally downloaded the zip files for 1999 and 2012 for fine particulate matter data. This is sometimes called PM 2.5. All right, so let's take a look at the basic data files that you get. So in this directory here, I've got the two files for 1999 and 2012. Now I should say that the original files are zip files, and each of the zip files come with two things. One is a text file with this .txt extension, and another is a PDF file which contains some documentation. So this is just the raw file that I downloaded from the EPA website. I haven't done anything to it. So let's just take a look at a couple lines of, let's say, the 1999 file. All right, so I'm going to take a look at this. And so one thing you can see is it's a little bit messy here, but one thing that's you can see, if I just pull this out a little bit, is that there's basically one record per line in this file. The first record here is kind of a header, and it tells you the names, basically gives you the names of the different columns. You can see each column is separated by a little kind of vertical line here, so that's nice to see. You can see that every record here begins with RD. All right, so these are called that indicates kind of the type of record, and that corresponds to the heading in the RD here. A heading over here. There's another type of headings here that corresponds to RC records, which are these guys over here. And if there were any RC records in this file, then they would have that heading. I don't believe that there are any RC records in this file, but we can just double check that by using a quick grep. So let's take a look at if any records start with RC. And nope, not for that one. And let's take a look at 2012. And none for that. So these are all RD records, and so we can use the RD headers to indicate what are the various columns. Okay, and so a lot of these columns are not going to be particularly important to us, but some of the things we're going to want to know are, for example, what state the record comes from, the county, the site ID indicates the kind of monitor within that county. And then most importantly is the sample value. So that tells us, what the level, that's the actual kind of mass of PM2.5 in micrograms per meter cubed. So that's going to be very important. And because we want to see if those levels have gone down over between 1999 and 2012. And the date of collection may also be important too. We'll take a look a little bit at that later. Now there are a number of other things here that indicate, certain records may have problems, but we're going to not worry about those at the moment. Those kinds of things may come in, may be important later on in a more in-depth analysis. Let's start up R here. So, okay. And the first thing I'm going to do is I'm going to read in the data for 1999. I'm just going to call it PM0. Which is, 0 meaning kind of like the first one, and I'll name the second one, PM1 or something. So I'll just use a straight read table here. I'm going to give it the 1999 file, and first thing I'm going to do is I'm going to ignore the lines that start with the hash symbol, and I'll kind of pick those up later. I'll say header equals false, and then sep equals, remember it's the solid line here, and then the missing values are indicated in this file with just a blank string. All right, so I'm going to read those in. You can see. That happens relatively quickly. Let's take a look. It's always good to check to see how many dimensions you got. So I've got about 117,000 rows, 28 columns. Let's take a look at the first few rows here, and you can see that I don't have the headers for the columns, so I'll get those in a second. But you can see that all these are different columns. And remember, the first column was this RD record indicator. And there are a lot of missing values here, which are not that important right now. So one thing we're going to want to do is kind of get the column names for each of these columns, so that we don't have to refer to them by V1 and V2. So if you recall, the column names come from the very first line in the file. So I'm just going to read one line of the first line. So you can use read lines for that. And I'm going to give it the file name, and it's going to tell it to read one line. Okay, so if I print out CNAMEs here, you can see first of all it's just a string, and it hasn't been split across, using the separator, because I didn't use read.table. I just read the line directly. So the first thing I'm going to have to do is split all the names out. So I'm going to use stir split for that. I'm going to split on this solid line, and it's a fixed pattern, not a regular expression. So now if I print out CNAMEs, you can see I get a character vector containing, for each element, it has the column name. Now stir split actually returns a list back, and so you're just going to want the first element of this list. And so now I'm going to assign the column names to this table to be this first value of this list here. So if I take a look at this data frame, you can see that there are all the column names are basically there. Now, one of the things that you'll notice is that these column names are kind of not valid, so because they have spaces in them, for example. And so one thing you can do to fix that is to use the make.names function. And the make.names basically takes an arbitrary string and turns it into a valid column name for a data frame. So now if I take a look at the first few lines here, you can see that it's replaced the spaces with dots. So now all of these are kind of valid column names for a data frame. So they'll be easier to reference in future kind of modeling or analysis functions. So the first thing I'm going to want to do is take out the PM2.5 variable. So that's the sample value column right here. And you can see the first three values here are missing, but then we've got 8.841, 14.9, etc. And those are in units of micrograms per meter cubed. So let's take a look at that column. Let's pull it out. I'll call it X0 here. And I'll just pull out the sample value column. And let's see what it is first. It's a numeric column. That's good. It should be numeric. Let's run a stir on it. Okay, so we got 117,421 values. It's a numeric vector. Let's do a little summary to get a 5-number summary of this data. So you can see the median is 11.5 micrograms per meter cubed. The maximum goes up to 157, which is quite a high level for a daily value. And there are also some missing values here. So let's see, so 13,000 missing values. Let's see kind of roughly what that means in terms of the proportion. So we can see is.na on this. And you can see that about 11% are missing. So we come across one interesting feature about this data set, which is that there are a number of missing values. And so one thing you have to ask yourself is, okay, are missing values something that I need to worry about? for the question that I'm interested in answering. Remember, we want to get a sense of, in general, does the whole country have lower air pollution levels in 2012 than it did in 1999? So the question is, does an occasional missing value on a given day in a given county or monitor, is that going to make a big difference? In particular, is having 11% of your values missing going to make a big difference in your analysis? So that's something to think about, because missing values can play a very different role depending on what kind of question you're trying to answer. And so you don't always, although missing values can be very inconvenient a lot of the times, they don't always cause a problem depending on what type of question you're trying to answer. All right, so now we've got the 1999 data. Let's read in the 2012 data here. So I'll call it PM1. I'll read.table it, and we'll do the same kind of approach. I'll comment out these rows. Header equals false. Sep equals the solid bar, and then any strings like that. Okay. So one thing you'll notice is that this is taking quite a bit longer than reading in the 1999 file. One of the issues is that PM 2.5 monitoring only just began in 1999, so there were very few monitors at that time. Of course, over the years, the monitoring has increased. And so now in 2012, there's a much bigger monitoring network available, and so there are going to be more observations. So let's take a look at how many observations exactly we have here. You can see it's quite a bit more. There's about 1.3 million records here, as opposed to the 117,000 records that we had before. So that may be a bit of a problem in and of itself, but I'll kind of put that to the side for now. So one thing I know is that the two files have the same column name. So you can see they both have 28 columns, and I know that the column names are going to be the same. They're both RD records. So I can just give the names for this data frame to be the same as the other one. So I'll do make.names here again. And you can see, if I take a look at the first few rows, all of the columns here. So you can see that the dates are now 2012, and the sample values here are the PM 2.5 values. So I'm going to grab the PM 2.5 values from here and take a quick check on what we have here. That's a numeric vector, 1.3 million elements, so that looks good. So now let's do a quick comparison of the 2012 and the 1999 data. So I'll do a summary on X1, and do a summary on X0. So that's interesting. So you can see that in the 2012 data, the median is about 7.3. And in the 1999 data, the median is about 11.5. So there does appear, on average, to be a decrease in the levels for the whole country in PM 2.5. You notice that there are quite a few missing values in the 2012 data set. We can take a look at what proportion that is. It's only about 5%. So there's actually, as a percentage of the total, there's actually fewer missing values in 2012 than there were in 1999. So that's interesting to know. 5% missing is probably not that big of a deal. Let's take a look at. So on first glance, it appears that the PM 2.5 levels have gone down over the years, and so that's good news for public health. Let's take a look. Let's see if we can take a look at a visual representation of this data. So let's take a look at a box plot. Let's see, box plot X0, X1, and let me bring this up. So it's a little hard to look at. There's a lot of skew in the PM 2.5 data, and so these they're right skewed, and so you can see that it's kind of all smushed down near zero, but then there's some very large values. One thing you'll notice is that the maximum value here is 909, which is an extremely high level. In fact, it's so high for the United States that we might think that perhaps it's an error, or maybe there's something wrong with it. 909 micrograms per meter cubed. Although it's not impossible, we do observe it in other parts of the world. We generally don't observe it in the United States unless, for example, there's some special or strange occurrence. So maybe we'll think about that value a little bit later, because since we're not really focused on extremes right now, we're looking at kind of the medians. So one way to kind of fix this box plot is to take a log of these guys. So let's take the log of x0. I'll do the base 10 log, and that will hopefully kind of even out the box plot a little bit. So here you can see that the 1999 data is right here, so you can see the median is about a log of equal to 1, which is roughly 10 micrograms per meter cubed, and then you can see that the black line, which is the median of this box plot, does go down quite a bit. Remember, this is on a log scale, so even a small change can be a big change in the absolute scale. But one thing you'll notice is that the spread of the data has also increased too. So even though the average levels have gone down, there are more kind of extreme values in the later data. And so that's interesting. We're not exactly sure what to make of it. So the next thing we want to take a look at is, if you notice in the summary for the 2012 data, there's negative values here. So that's a little bit strange. So one of the things about measuring PM2.5 is that we measure the mass of it kind of per unit of airflow. So basically the idea is that there's a filter and there's air being sucked through the filter, and then the particles collect on the filter, and we weigh those filters to see how many particles kind of have landed on the filter. And so because of the way that it's measured, you really can't have a negative measure. You can't have negative mass. And so if there's a negative value for the PM2.5 variable, that's a little strange. It's a little unusual. So let's take a look. We can take a look at that. And see, kind of maybe get a sense of what's going on. So let's pluck out the values. Let's take a look one more time at the summary. Let's pluck out the values that happen to be negative. So I'll create a logical vector that is true or false depending on whether the 2012 PM2.5 value is below 0. So if you take a stir on this, you'll see that it's true false vector. So if I take the sum of this, NARM equals true, you'll see that there are about 26,000 values that are below 0 or negative. So that's a little bit strange. Let's see what the proportion this is. So it's about 2% of the values. This is not a really large number of values. And so maybe it's something that we don't even care about, but it may be worth taking a look at it. So in particular, it may be interesting to see whether there are negative values at certain times of the year, or maybe only the negative values occur at certain locations or times. So let's take a look at the dates of the measurements. So I'll pull up the dates column. And if you take a look at this, first of all, you'll notice that it is an integer vector, right? So these are coded as integers by default, which is not going to be as useful for us. So we want to be able to convert them into dates. And so one thing you'll notice is that they're in a year. So the first 4 digits of the year, the second is the month, and the second is the day, right? So here we've got 2012, and then January, and then 28th, right? So let's take a look. Let's convert those guys to date variables. So we do as.date, and it's going to be in the year, month, day format. Okay. Now it's a reasonably long vector, so it's going to take probably a few seconds on a reasonable computer. Now take a look at the dates vector. So you can see now it's in the date format. So let's take a look at just a histogram of the dates to see kind of where the collection occurs. We can do it by month, and you see that most of the measurements are occurring in kind of the in the winter months here. So winter and spring months here. So let's see where the negative values tend to be. So we'll do hist on dates and negative. So this only makes a histogram of the dates where the negative values occur. Oops. And I'll say month. And you can see that the negative values tend to occur, seem to occur more often in the December, January, February types of months. There's a little bit of a spike here in April, kind of May, June type period. So it's interesting to see that there aren't many negative values here in the summer months here. And so it's not entirely clear what this tells us, but it may be worth investigating. One issue with PM2.5 is that in many areas of the country, it tends to be very low in the winter. and high in the summer. And so typically when pollution values are high, they're easier to measure, and when they're low, they're harder to measure. So maybe some of the negative values are just kind of a measurement error when the values tend to be very low. But given that it's only 2% of the data, I'm not going to spend too much time worrying about it at the moment. It may be something that we worry about later. So one of the things that I think would be interesting to do is, rather than look at the air pollution levels for the entire country and say, okay, well, the median for the entire country has gone down between 1999 and 2012. Why don't we pick out one monitor and see whether we can see a change or decrease in the levels just at that one location, and so. That way, we can kind of control for the fact that there's different monitors at different times. Now, one thing we have to do is we have to find a monitor that was kind of out there in 1999, and then it was also out there in 2012, because the networks changed quite a bit. And so we're going to pick a state and then try to find a monitor in that state to see whether or not the pollution levels have gone down. So I'm just going to pick New York State because that's where I'm from, and let's try to find a monitor there where we can look at the change in the levels. So the first thing I'm going to do is I'm going to subset the PM data to look at the all of the kind of monitors in New York State. So I'm going to take take the PM0 data frame, and I'm going to subset on state code equals 36, which I just happen to know is New York State because I do this a lot. And I'm going to pluck out the county code and the site ID columns. And then I'm going to do the same thing for the 2012 data set here. Okay. So, and then what I'm going to do is so if you take a look at site 0, you can see it's a 2-column data frame, and it just has the county code and the site ID. What I'm going to do is create a special kind of variable that's just the county code and the site ID pasted together, right? And so we can literally use the paste function to do that. So I'm going to kind of replace this guy with paste, and I'll take the first column and the second column and separate it with a period. And then I'm going to do the same thing for the 2012 data. All right. So now if you take a look at site 0, it's a character vector. You can see that it's the kind of county dot and then the site ID. If you look at this, it's kind of the same thing, right? So one thing you'll notice is that the 2012 vector, it only has 18 elements, so there are only 18 county and site ID combinations, whereas the 1999 data had 33 of those combinations. So the only thing, so basically what we want to do is we want to see, well, what is the intersection between these two guys? So where, which county / monitor ID numbers exist in both sets. We can just use the intersect functions for that. And I'll assign it to an object called both. So these are the monitors that are in both the 1999 and 2012 data sets. So if we print this out, you can see that there are 10 monitors, 10 county / monitors that are in both data sets. So that's good, at least that there are a few that we can look at across the time period. Now, one of the things that would be useful is if we chose the monitor that is first of all in both time periods, but also had a lot of observations that we could look at. So let's take a look at how many observations are in each of these monitors and in each of these time periods. Okay, so the first thing we want to do is we want to figure out how many observations are available at each monitor. So I'm going to create a new variable called county.site, which is just what we just created. So it's the county code pasted with the site ID, but I'm putting this in the original data frame here, and I'm going to do it for the 2012 also. And then what I want to do is I want to subset this data frame to be just New York State, right? So I'm going to subset PM0 to be state code 36, and county site is one of these special monitors, which is in both data sets. All right, I'll do that for this guy here. And now so if you take a look at this, it's the same data frame, but it's only the rows that are in New York City. So you can see that the state code here now is 36, right? So what I want to do is I want to split this data frame by the kind of monitor. So I want to split it into separate data frames by each monitor and then count how many observations there are in each of them. So I'm just going to do a split this data frame by this county site variable. Right, now actually that was not particularly useful because it just spit out a whole list of data frames and I don't really know what happened there. So what I want to do is I want to sapply over all these data frames and count the number of rows that there are. Okay, so that gives me the number of observations that are in each of these data frames. So you can see that, for example, County 1, Site 12 had 61 observations and County 1, Site 5 had 122. So now I want to do the same thing for the later period. Excuse me. I had to change this too. And you can see now that in County 1, Site 12 only had 31 observations in 2012 rather than 61 in the 1999 data set. So I think that the county/monitor that I'm going to pick here is going to be County 63 and monitor 2008. So let's take a look at those guys and see what we can look at in terms of PM trends. So I'm going to call a new data frame called PM1 sub. I'll subset it, PM1. County code is 63, and the site ID is 2008. All right. And then I'm going to do the same thing for the 1999 data. I know that they're both there. I look at PM1. I know there's 30 observations. And for PM0 sub, there should be 122. There you go. So the thing we're going to do now is we're going to take each of these data frames and we're just going to plot the data, the PM 2.5 data, as a function of time. So there's going to be like a little time series here. And on the x-axis is going to be the date. And on the y-axis is going to be the level of PM 2.5. And we just want to get to visualize whether or not we can see that the levels of PM 2.5 have gone down over this kind of 13-year period at this particular monitor. Okay, so we're going to make some plots to do that. So the first thing we need to do is to get the dates out so we can plot the data as a function of date. So dates, I'll create a dates vector here from this PM sub data frame and get the PM 2.5 data out. So if I make a plot of the dates, you can see, well, first thing you'll notice is that the dates are not coded properly. They're integers here, and so we need to convert them into dates. So I'm going to do that right now. And they're in year, month, day format. So now if I make this plot again, well, first of all, you can take a look at the new variable. And if I make this plot, so it's in date format now. And you can see now the plot makes more sense. The x-axis is coded appropriately. And you can see that the data are kind of bouncing around all over the place, somewhere between 4 and 14 micrograms per meter cubed. So this is the 2012 data. So let's do the same thing for 1999. We'll convert these guys to date format since we know we have to do that. And let's make a little plot here. Oops, I didn't get the PM 2.5 data. All right, so let's make a plot of the 1999 data. So you can see that again. First of all, you'll notice that the data are only actually recorded starting in July through the end of the year. So only about a half of the year of the data is collected there. And you can see that they range from roughly, say, 5 micrograms per meter cubed to about 40. So, now, of course, it's a little hard to look at the plots separately, so why don't we make a plot that kind of puts both 1999 and 2012 on the same panel. So we need to use par for that, and we'll say mf row is 1, 2. So this says 1 row, 2 columns. And I'm going to adjust the margins a little bit to create more space. So first I'll plot the 1999 data on the left-hand side here. change the plotting character for fun. All right, and then I'll plot the, I'm going to put a little line here at the median for that year. Okay, so that gives me the median, about maybe 10 point so micrograms per meter cubed. Now let's plot the 2012 data. And we'll plot the median. All right, so that's well, that's a little bit unusual. It looks like the values are going up between the 2 years, but actually, so it's a little bit misleading because you'll notice that the y-axis for the 2012 data is totally different from the y-axis for the 1999 data. And so, even though it looks like it's going up between the two time periods, it probably actually is going. If you look at the median here, it's a little over 10, and the median here is quite a bit under 10 actually. And so, this picture is by itself is a little bit misleading. So what we need to do is we need to put the two plots on the same range. So let's do that by calculating the range of the data set with the range function, right? So let's take a look at the range of x0 sub and x1 sub together, and we'll remove the missing values. And you can see that it's between 3 and 40 micrograms per meter cubed. So let's assign that to this to a variable called RNG, and now we need to remake the plots to be to kind of fix the range here. So I'll set par just in case. I don't need to do this actually. So let's plot the dates and PCH equals 20. But now I'm going to set ylim to be equal to this range, okay? And I'll set the AB line, h equals median. All right, and then I'm going to do the same thing, but for the 2012 data. And remember, I'm gonna keep the range here to be the same, and I'll set the little horizontal line here. And now you can see it makes more sense, right? So you can see that the horizontal line, the median, is going down between the 2 years at this monitor. And more interestingly, actually, for me, is the fact that you can see there's a huge spread of points here in the 1999 data, and there's a relatively modest spread of points for the 2012 data. So what this means actually is quite interesting, is that not only are the average levels going down, but these extreme values are also coming down across the years too. So on average we're kind of breathing in lower levels of pollution, but we don't get these huge spikes on a daily basis like we used to get in 1999. So those two kind of facts are quite interesting because they kind of address two different types of problems. One is more of a chronic problem of having kind of just on average very high air pollution levels, and one is more of an acute problem where you get these really big spikes that can cause different types of health problems. And so we've reduced the average levels and the spikes at this monitor, so that's quite interesting. So one thing I think, so the last thing I think I want to look at is to say, okay, well, let's not look at the whole country, but also it's not that useful perhaps to look at just one monitor. And so why don't we look at individual states in the country? So we'll look at the different states to see how the individual states have improved or not across the years. And one of the reasons why this is important is because the states are actually where a lot of the implementation of the regulations occur. So when the EPA sets the national guidelines for air pollution levels, it's up to the state to figure out how it's going to kind of come into compliance with those guidelines. And so it'd be useful to kind of develop a summary at the state level to kind of see what's going on at this kind of very important level. And furthermore, the state is somewhere in between, the whole country and an individual monitor. Okay, so what I want to do is I want to create a plot that has kind of the state averages for 1999, and then the state averages for 2012, and then I just want to connect the dots to connect each state to see whether it's going up or it's going down or maybe staying the same. So that's the kind of plot I want to make. So let's figure this out. So I'll change my plot window here. Bring it back. So first thing let's take a look. Remember the data has a column here, which is the state code, and so every state will have a code there. And so what I want to do is I want to take the sample value here. So this is the PM2.5 value, and then I just want to take the average value by state, right? So this is the kind of thing that's going to require the tapply function, where the tapply, remember, takes the mean of a vector within subgroups determined by another vector, right? And so this is the perfect job for tapply. So what I'm going to do is I'm going to create a vector that I'll call mean 0. So this is the mean of the 1999 data, and I'm going to base it on the PM0 data frame, and I'm going to tapply the sample value based on the state and within subsets of the state code, and I want to use the mean function. And I'm going to get rid of missing values here. Okay. So if I take a look at this guy now, you can see that there are 53 elements here, and these are the means of the individual states. Okay. If I take a summary, you can see that they range from 4.8 micrograms per meter cubed to 19.96. Okay. So now we need to do the same thing for the 2012 data. So I'll just let me just go up here, and I'll just change this to a 1. Same operation. We can take a summary of this data. You can see that it ranges from about 4 to 11. Okay, so and the median is definitely lower. The median in 1999 was 12, and this is the state average. This is kind of the median of all the states, and the median of all the states in 2012 was 8.7. So now I want to create a data frame for each of these guys that has the kind of the name of the state and the ID of the state and their kind of average PM 2.5. So I'm going to create a data frame called D0 with a variable called state. It's going to be equal to the names of this guy, and then mean, which is the value, and then I'm going to do the same thing for the later data. So you can look at D0, you can see that there's the state and then the mean. Usually D1, it's also the state and the mean. Now I just want to merge these guys together. So I can use the merge function on D0, D1, and I'm going to merge it on the state name. Oops. A little typo there. So if you look at the merged values, you can see there are 52 rows. And if you look at the merge value, now you can see that the mean x, so this corresponds to the 1999 value, and this corresponds to the 2012 value. So now I've got a data frame which has the state code. It has one row per state, and then each row there's the kind of the state average for 1999 and the state average for 2012. So just basically what I want to do is create a plot that plots those state averages and then connects them with a line. So that's the last thing I'm going to do here. So I'm going to reset my par to just one plot here instead of a panel plot. And then with this merged data frame, I'm going to plot, I know that there are 52 values, so I'm just going to plot the 1999 values in one column. That's all right. And I want to set the xlim here, so I want to make room because I know I'm going to plot the 2012 values later. So I want to set the xlim to say let's be, and then like that. Oops. And all right, so you can see I've got my 1999 values right here, and then I'm going to do the same thing, but instead of plotting, I'm going to use points to add the points for 2012. And this is the third column of the data frame, and I don't need this xlim here because I'm using points. And if I bring the plot over here, you can see that I've got my plot. So you can see that the data has kind of gone down quite a bit. We saw this already in the individual monitor data. So all we need to do now is kind of connect the dots here. And so we can use the segments function for that. So we give the x coordinates, the y coordinates, and then the second set of x coordinates, which would be 2012. And Eric, now we can see, okay, so this is quite interesting. Now we can see that most of the states have gone down. You can see this line here has gone down. These lines here, some states have gone up. But the vast majority of these states appear to be going down. The one thing you'll notice is that there appear to be some lines kind of going off the chart here. That's because I didn't set the y-lim to be equal to the full range of the data set. So we could have fixed that, but I won't bother with it right now. We can fix it later. But now we can see that each of the states, how they progressed over the many years here. So some states kind of have barely really moved at all. So this state right here has barely really moved at all. And the lines kind of connecting the dots help us see what the trends are at the individual state level. All right, so that's kind of a first exploratory analysis of some air pollution data in the United States. If you were just to summarize, the basic question we were trying to answer was, have particulate matter levels decreased between 1999 and 2012, and we looked at it for the whole country between 1999 and 2012. We looked at it for an individual monitor between those two time periods, and we looked at it for individual states. And so through a combination of kind of summaries, 5-number summaries, box plots, scatter plots, things like that, we can get a very nice look at the data and get a sense of kind of what kinds of questions we can continue to ask and what kinds of things we should follow up on. So that's just a kind of a simple case study of how to do exploratory analysis, and I hope you find it helpful.